In this final video on intermolecular bonds, we're going to talk about one special type of intermolecular bond, which is the hydrogen bond. Now, if you remember back to that summary slide where I showed all of the different types of interactions between molecules and ions and atoms, etc., we looked at intermolecular bonds and said, well, they're all very weak compared to, say, ionic bonds and covalent bonds. And we collectively called a lot of the intermolecular bonds van der Waals forces, and we said that they might have strengths of, say, 1 to 5 kilojoule per mole, something like that. Well, the hydrogen bonds sort of stood apart from this, and I said at the time that they were a special type of permanent dipole bond, which they are, but they weren't really classified as van der Waals forces. And this is really because of their strength, and as you'll see in a second, they're slightly distinct from other types of intermolecular bonds. So hydrogen bonds can be up to, say, 20, maybe even 30 kilojoules per mole, so are a lot stronger than the other types of intermolecular bonds that we've seen. So we've got to be able to describe their formation, and in particular we'll look at water and ice, and some of the implications of hydrogen bonding in water there. And this all links in to be able to explain the relative boiling points of substances in terms of their intermolecular bonds. So it's another type of intermolecular bond that we need to consider that may form between molecules and affect the amount of energy that's needed to separate them. Well, there we go. So there's the hydrogen bonds being drawn there between water molecules. So what exactly is a hydrogen bond? Well, as I said, it's a special case of a permanent dipole interaction. And it's the force of attraction between a partially positively charged hydrogen atom that's attached to a small electronegative atom such as oxygen, nitrogen or fluorine, and the lone pair on a small electronegative atom in a neighbouring molecule. So as you can see here, this is a hydrogen bond between two water molecules, and our conditions for this again, so we make this really clear. In order to form a hydrogen bond, you need a hydrogen atom that's been made partially positively charged by being attached to a highly electronegative atom, and we are only talking fluorine, nitrogen or oxygen here. If we look here at the electronegativity values, you can see here oxygen, nitrogen and fluorine being the most electronegative atoms in question. Chlorine has an electronegativity similar to nitrogen, but chlorine doesn't fulfill this second requirement, which is that the highly electronegative atom must be small. Chlorine obviously is larger than, say, nitrogen here with similar electronegativity. And it must have one lone pair of electrons. The lone pair of electrons is going to be involved in the hydrogen bond to the partially positively charged hydrogen on a neighbouring molecule. And why it needs to be a small electronegative atom, it's because, remember, electrostatic attraction is greater when the charges are closer together. So fluorine, nitrogen and oxygen can approach close enough to the hydrogen atom in order to form this very strong interaction. Now, why is it so strong? Well, hydrogen's a bit of an oddball. It doesn't have any shielding electrons. So if you have two electrons, say here in the bond between oxygen and hydrogen, if the electron density mainly sits on the oxygen, because the oxygen is a lot more electronegative than the hydrogen, it essentially leaves a partially exposed nucleus on the hydrogen because there's no other electrons there on the hydrogen. So it makes this very delta plus indeed. Now, if you have a small electronegative atom with a lone pair on it, then what you've got, because this will be delta minus as well, you'll have a region of very concentrated negative charge. So if that can approach the very delta plus hydrogen, then you've got a very strong electrostatic interaction there. And that is the hydrogen bond. So they're typically a lot stronger than permanent dipole interactions. Now there's just a little note down here in this box, that the OHO bond angle in water here is 180 degrees. So what that means here between this oxygen, this hydrogen and this oxygen, the bond is straight. Now you can understand why it's straight if I tell you that actually current research suggests that the hydrogen bond has about a 10% covalent character. What that means is that this lone pair is almost trying to form a covalent bond here. Now if you go back to thinking about shapes of molecules, what that means is around this Around this central hydrogen atom here, you've got two regions of electron density. If they repel each other to occupy a position of maximal separation, blah, 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 that means that this would be linear and there would be a 180-degree bond angle there. Now, never say that 10% covalent character in an exam, because the examiner might think that you're confusing it with a covalent bond. But it just gives you an explanation of why these things are very, very directional, because they're almost sort of trying to be covalent bonds, if you like. It's an electrostatic interaction between this lone pair, which points in a particular direction, and the hydrogen atom. So it's not a general electrostatic attraction. Now, in terms of drawing this in the exam to maximise marks, sometimes they give away 4 marks for this. So key features that we've got to put on this. As I said, the bit that I've circled here, this is the bit that has to be straight. So from the oxygen to the hydrogen to the oxygen here. You have to indicate the hydrogen bond itself, and you can do that with dashes this way or dashes the other way. Lone pair on the electronegative atom, so that's critical because it is this electrostatic interaction between the lone pair and the partially positively charged hydrogen atom, and you've got to show the partial charges on the atoms involved in the hydrogen bond. I'd be safe and I'd show them on all of them, because I suppose if you're putting a delta minus there, why is it delta minus? Oh, because these are delta plus there. So it's very easy, really, to get 4 marks in the exam there. There's a little video here that I'd quite like you to watch. I can't click on this and show the video in here because it won't play the sound. But I've included this on the email that I sent you, so you can directly click on the link there. It's going to go over some of the properties of water and talk about why hydrogen bonds are important with the properties of water. Watch that and then come back to this, so just pause this for a second, and then I'll summarise the key one that you need to know for your syllabus, which is to do with water and ice and the density of water, and relative densities of water and ice. So now you've watched that, the key thing that comes out of this as far as you're concerned for your syllabus is the difference in the structure between liquid water and ice. Now in ice, as you would have seen on the video, what you've got in the water molecule is you have 2 lone pairs and you've got 2 hydrogens. So you've got the potential on a per molecule basis to be forming 4 hydrogen bonds. What this means, as we said, because they're very directional, is that the ice adopts a very open structure. When you melt ice, though, you're obviously disrupting some of those hydrogen bonds. And in disrupting the hydrogen bonds, what you're actually doing is you're allowing the structure to collapse and the water molecules to approach each other more closely. Now, of course, there will be some hydrogen bonds still existing between the water molecules, but there'll be, on average, fewer than 4, meaning that it'll have a structure in which the water molecules are closer together. And in that case, then, will be far more dense, which is unlike most typical substances, which just get denser and denser as they get colder and as they go from a liquid to a solid. This graph here, though, does show that it's slightly more complicated than that, in that the maximum density of water is about 4 degrees C. This is because as you cool water, just like normal substances, its density increases as the molecular motions slow down and decrease. But at about 4 degrees and just below 4 degrees, some of the regions within the water structure start to adopt this open structure shown in ice. So what that means is the density starts to then decrease. So the maximum density is at 4 degrees, just before the freezing point. Now, in our next lesson, what we'll do is we'll put our understanding of intermolecular bonds and their hydrogen bonds all together, and we'll look at explaining some quite complicated trends in boiling points that should test our understanding of all of this.